Hello, everyone. Welcome to today's session. We're so glad that you could take time to be here with us today. Before we get started, I do have a couple of housekeeping announcements. You are going to be muted during this presentation. If you'd like to ask a question, we ask you to enter it into the online Q&A box. And we will save time at the end of the presentation to address as many questions as possible. And this presentation is being recorded and will be made available on the California Labor Lab and Center for Occupational and Environmental Health YouTube page in the next 5 business days. And all participants who logged in with their registration email for the full live presentation today will receive an email tomorrow with a link to an evaluation form that will qualify you for a certificate of completion worth 1 continuing education contact hour. Once the evaluation is completed, you'll be able to access and print your certificate. Without further ado, I'm going to hand it over to Dr. Ed Yellen to introduce our speaker for today.
Thanks, Michelle, and it's my distinct pleasure to introduce Carisa Harris. I know her well because I was on the search committee that found her. We didn't have to look very far, and we were glad we didn't. Carisa handles very many roles in the Berkeley UCSF orbit. She is an esteemed professor of occupational environmental medicine at UCSF, where she directs the ergonomics lab in the Richmond Field Station and is well known for her and well funded for her work in ergonomics, some of which you'll be reporting today. But she's also now the director of the Northern California Center for Occupational Environmental Health, the 3-campus Berkeley, UCSF, and Davis organization that fosters a healthy work environment for the people who reside in these areas and the research community that is devoted to that issue. And as part of that, she's the principal investigator of the ERC, the Education and Research Center, that runs out of the Berkeley campus and it organizes the training of our superb pre and postdoc community here. So lastly, and I think not leastly, she is the Associate Director for Research of the California Labor Lab, and we call upon her expertise in that on a daily basis. So I could go on, but you get the idea. She is very good at very many things. And without further ado, Carisa, the floor is yours.
Thank you, Ed. And thank you, Michelle. It's really a pleasure to be here and has absolutely been an honor to work with you all. I'll go ahead and share my screen. Okay. So today I'm going to be speaking about the application of exoskeletons in construction to mitigate heavy workloads. There is a long list of collaborators that I want to thank. We have our partners at Virginia Tech who have been with us throughout this project. We also have our partners at CPWR who have been the funders of this project along with NIOSH. There have been many students along the way who have learned through this project, and I want to thank them for all their hard work. I have no personal conflicts of interest to disclose, but the UC Human Factors and Ergonomics Lab is supported by these organizations. I'm going to do a little bit more background than I normally do, just to make sure that we're all on the same page with what musculoskeletal disorders are, what risk factors are associated with them, and also what exoskeletons are. And then I'm going to talk about a project that we've been involved with for the last 5 years on exoskeletons and their implementation into construction work. So work-related musculoskeletal disorders account for over 600,000 injuries annually and present about 34% of all lost work days. Employers spend about $15 to $20 billion in direct workers' compensation costs each year. And indirect costs associated with those injuries can be up to $45 to $54 billion annually. They're essentially responsible for 1 out of every $3 spent on workers' compensation, which really underscores their financial burden on employers. as well as workers. There's work-related musculoskeletal disorders are essentially injuries or disorders of tendons, cartilage, muscles, joints, and nerves that are caused or exacerbated by working conditions. There's two different types. One is caused by sudden force, and this is more of your impact traumas. And those are not the injuries that we're going to be talking about today, although we certainly want to make sure that something like an exoskeleton doesn't increase one's risk for some sort of sudden injury. We are going to talk about overuse injuries, tendinitis, tendinosis, nerve entrapments, myofascial pains, low back pains. Those are all examples of what we call overuse injuries. And there are well-known risk factors associated with increased occurrence or incidence and severity of work-related musculoskeletal disorders. These include force, so lifting heavy loads, repetition, doing something over and over again, awkward postures, either that are deviating from sort of a neutral position or postures that are sustained for long periods of time. Contact stress, meaning having some sort of sharp object sort of on a certain body part where maybe a nerve is close to the surface. And then environmental factors such as vibration, cold temperatures, and lighting. And combinations of these exposures can increase one's risk for an injury. And we like to think of this in terms of demand of the task and capacity of the person performing that task. So here we see two of the exposures. So force, like the weight of a load that might be lifted, such as a tool used in construction, and then say the frequency of those lifts. And what you see is that if someone's capacity to do some work is greater than the demand of the task, then that task will be acceptable for them and they'll be underneath this line and won't experience an injury. If, however, the demand of the task exceeds their capacity, they can be injured. And that can happen either acutely, meaning they lift sort of a very heavy load very few times, or it can be due to repetitive nature, where they lift a lower magnitude of load multiple times. In construction, musculoskeletal disorders are common. Construction workers continue to experience high rates of injuries, 32.5 per 10,000 FTEs. And this is higher than most other industry sectors. The back and shoulder are two of the most impacted regions. Back injuries account for 43% of all cases, with a median of 8 lost work days. And shoulder injuries account for 16% of all cases, with a median of 25 lost work days. And I do want to talk about some of the characteristics of construction work that are really relevant to implementing something like an exoskeleton as a way to mitigate exposure. In 2023, there were 919,000 construction businesses in the United States with 8 million employees. And they were responsible for creating $2.1 trillion in structures. The majority of these companies are small construction companies with less than 20 employees. They include specialty trade contractors, residential builders. There's medium-sized companies, which include between 20 and 100 employees. And then you have some of the large construction companies who have more than 100 employees. They're fewer in number, but they play a really significant role in infrastructure and commercial projects. The fact that there are these very different kinds of companies means that the strategies to implement something like an exoskeleton, or any intervention for that matter, must be really different, given that these companies are all extremely different from one another, which we'll go over more in a sec. So if we look at company size and we think about something like health insurance, so we know that construction workers are at high risk for an injury. Where are they getting their care? Well, we can see that company size matters when it comes to something as basic as even having an employment-based health insurance. As the company size gets larger, you can see that a larger percentage of construction workers are provided with that basic health insurance, but it's these small employers, and remember, they make up 90% of the companies that have, a smaller percentage of them have that health insurance. We also see differences in health insurance by race, with Hispanic workers having a smaller percentage of them having health insurance compared to their white counterparts. And we also see that being unionized matters. So unionized workers typically are more likely to have this employment-based health insurance versus non-unionized workers. When we look at age distribution in construction, we can see that there's a rapid increase in construction workers kind of in the 20s, and then it starts to plateau in the mid-20s to mid-40s, and then will start to decline. And this is really important because construction industry labor projection models have identified a shortage of workers, up to 650,000 last year alone, to meet the increase in critical infrastructure needs across the United States. And so if we could find a way to hang on to these workers longer, then that would be really beneficial for the industry and for the worker. When we look at construction workers by sex, we can see that women make up a very small percentage of workers in construction. Depending on the trade, they either have more or less representation. They tend to be most highly represented among painters, and less so in areas like electrician, carpenters, and foremen. You can see overall the percentages of female are extremely low. Now, to address construction worker shortages, we believe it's critical to make construction work more acceptable for a more diverse population of workers. And that would allow us to retain more workers, such as aging workforce, as well as attract new ones, perhaps more women into the trades. And so one of the ways that we think this could be done is through the application of industrial exoskeletons. There are different kinds of exoskeletons. There are ones that help to elevate the upper extremity, meaning they support the arm as one is lifting or doing this overhead work. There's ones for the back as well. And you can see that there are even leg supports and power gloves and exoskeletons that actually hold the tool instead of someone's arm. Essentially, these wearable exoskeletons, they are devices that work with the user, and they all have something in common, which is to augment, reinforce, and restore human performance. These exoskeletons that I'm showing in this picture are what we call passive exoskeletons. And so they use sort of mechanical characteristics of the exoskeleton to provide this support and don't need any sort of battery pack or power source that's external to the exoskeleton. And so there has been a lot of research on exoskeletons and how they might reduce the risk of work-related musculoskeletal disorders. They have been shown to lower muscle activity, particularly around the shoulder. Our project has included both back and shoulder support exoskeletons. I'm going to focus today more on the shoulder, or what we call arm support exoskeleton. And that's what you see here in this picture, with this person holding a drill with this arm support exoskeleton, providing, again, support for their arm in this position. And so many studies have shown that this kind of device reduces muscle activity, say, of the anterior middle deltoid. They've been used in manufacturing lines, such as the automotive industry. The tricky part is that there are variations in construction tasks, construction environments, company sizes, and worker demographics, all of which present challenges to how we would implement arm support exoskeletons in construction. With our Virginia Tech partners, we collected information on a survey to evaluate what the expected benefits, barriers, and what we should be thinking about as far as technology adoption. All different things that we wanted to consider when looking to implement an exoskeleton in construction. And it was interesting. We found that some of the expected benefits were everything from reduced musculoskeletal injuries or disorders to better worker retention or productivity gains. From barriers, there were a lot on exoskeleton technologies and how durable they would be. Would they be accepted? Would people be able to use them? How easy would they be to use? How easy would they be to fit? And how safe were they? Were there going to be issues with falls, catch and snag risks, et cetera? As far as adoption, things like how much they cost and what kind of training would be needed and provided to use them were all areas of concern. And so based on this, we submitted a project to CPWR and NIOSH to support the evaluation of exoskeletons specific to construction. I'm going to talk about three of the aims. The first one where we obtained input from construction industry stakeholders. The second, where we looked at the efficacy of exoskeletons for construction tasks. And then the third aim was where we looked at perceived safety and effectiveness and acceptability. And then I'll finish by talking about the next 5 years and what we're going to be doing to evaluate exoskeletons in the field. So again, some of the potential benefits and limitations of the technologies that we wanted to hear more about were the potential benefits for augmented capacity and performance, the barriers specific to usability, safety hazards, and durability, and then the adoption. And this had to do with people's perceptions on training, cost, and how well they would be accepted. And so this particular portion occurred right during the pandemic. And so we had to switch from sort of an in-person training and evaluation and survey to one that was online. I'm going to take this moment to thank Alan Barr, who has been really critical in helping with this project. And he actually created this video to walk people through what an exoskeleton did before asking them specific questions about the exoskeleton and what their perceptions were of it. We got input from 361 respondents. 24% were Hispanic, 77% were male, and there was a median age of 47 years. 66% had more than 15 years of work experience, and they represented companies from various sizes. Interestingly enough, 36% had heard of workers using an exoskeleton, and about an equal number had never heard of it at all. And we asked them about their discomfort in the shoulder and back due to construction work. And you can see that using a numeric pain scale, with 0 being no discomfort at all and 10 being extreme discomfort, there are quite a few people in moderate to severe pain. And this is really important because we feel that this group of people might actually be more ready to accept something like an exoskeleton. We had a great participation from a variety of trades. And so this word map just shows essentially represents the number of people that responded and the various trades that they represented. Again, you can see that the shoulder and back discomfort, those experiencing 5 or greater, was quite large. And when we asked them about the work demand, 60% rated their work as very to extremely challenging. We also asked them about their fatigue at the end of the workday and the work week. And you can see that if 0 is no physical fatigue and 10 is extreme physical fatigue, you can see that there's a large number of people that experience a lot of fatigue, physical fatigue, by the end of each workday in orange, and then even more fatigue at the end of each work week. When we asked them what they felt contributed to fatigue, it was things like repeated motions, extended work hours, heavy tools and equipment, and strenuous postures that we felt would really be important to evaluate, because these are things that exoskeletons could help mitigate. The hot temperatures was also interesting because arm support exoskeletons can make you hotter. They're worn, they sometimes feel a bit like a backpack. And so this was important for us to evaluate as well. We looked at receptivity on 4 scales, the potential benefits, barriers, perception of exoskeletons, and readiness to use. These were scored based on responses, and each category included things like, I believe it'll make my job easier, I believe it'll reduce fatigue, I believe I'll be more productive, questions of that nature. When we combine the scores to look at benefits, barriers, positive perception, and readiness to use, we actually stratified it across people who reported lower fatigue, 0 to 5, to moderate fatigue, 6 to 7, and then extreme fatigue, 8 to 10. And we do see that the perceived benefits and the positive perception of exoskeletons and using them in construction is greater in those that are experiencing extreme fatigue. And so that's, again, something that we want to keep track of and evaluate more as the study goes on. We also looked at trades. There wasn't a huge difference by trade, but we did see that like carpenters and tile setters and roofers had a slightly more positive perception. And when we see barriers, we see things like electricians identifying more barriers, obviously with the concern on snags and electrocution and being able to fit in constrained spaces while doing their work. Other concerns were things like slips and trips, trench collapses, working on a scaffold, electric shock, protecting the exoskeleton from dust. Again, this temperature, and would it increase their risk of getting struck by or caught in between objects? And so to summarize from AIM-1, what we found was that sharing and fitting the exoskeleton was identified as a big barrier. Although 97% agreed that they would share an exoskeleton, 80% agreed that it would make it really difficult to refit or use. And they didn't feel like there was enough information to guide them on how to fit it and select support levels. And so given that 90% of construction companies are small companies and don't have necessarily a safety person that could be taught how to fit exoskeletons, we saw this as actually a very large barrier. Some of the common safety concerns included slips, trips, and falls, struck by caught in between accidents, issues with scaffolding and trenching work, and overall just reduced mobility from wearing the exoskeleton. So taking this knowledge into the laboratory testing was really important. And I do just want to take a moment to underscore the importance of getting the voice of the workers and the perceptions of the workers to help identify what should be evaluated in the lab. And we actually changed a couple of our priorities based on what we found in AIM-1. So in AIM-2, we wanted to look at specifically how could we normalize fit and support so that it made it easier for construction workers to put on and set up the exoskeleton. And it also made it easier for construction workers to identify what level of support was best for different tasks, given that they have so many tasks that they perform. We also wanted to look at usability and safety to really understand how the exoskeletons impacted them. And then we wanted to be able to identify optimal settings of the exoskeleton based on different task characteristics. So exoskeletons have 2 primary components of fit. So one is the setup of the exoskeleton to actually fit the body size of the person, and that's what we call a fit. And then there's also the support, and the support is how much support or torque is it producing against the arm, and essentially how much assistance is it providing. And so we added this component because we felt that being able to increase the efficiency and optimization of fit and support level settings was really critical. And so we identified an approach based on the subject's height, weight, and sex to be able to do this. Again, this is largely the work of Alan Barr. He used or he created prediction equations based on height, weight, and sex, and then generated outputs for various settings. This allowed us to identify the specific settings based on the exoskeleton that would fit a certain person of a certain height, weight, and sex. The next thing is that that exoskeleton was adjusted and then put on the person, and the predictions were validated by an expert who checked on certain criteria that differed for each exoskeleton and was based on the specific exoskeleton manufacturer's guidelines. So just to give you a quick idea of what this looked like, I'm not going to go into a lot of detail, but we used a database of anthropometric measurements, meaning measurements of the body. We used these types of measurements like bideltoid length, shoulder to elbow, the height of to the neck, and as well as the hip. And we were able to get the proper dimensions based on the person's height, weight, and sex, and then identified what those coefficients were and put them into an estimation equation to get certain dimensions that we were interested in. And so Alan did this for multiple exoskeletons, and he also did this for all the available settings of each exoskeleton. And so just to give you an example, to predict spine length, we have spine height here, and then available exoskeleton settings. And the prediction model would say, okay, given the person's height and weight, the spine height is estimated to be 21 inches. And so the exoskeleton setting for the spine that should be chosen is essentially somewhere around number 6. He used a force gauge to identify at a 90-degree angle how much torque was provided at different settings with different arm lengths. And again, created different algorithms to identify how much force was provided given those settings. And then the person was fit in the exoskeleton, and there was a float test, meaning the person put their arms at 90 degrees, were asked to relax their shoulder muscles completely. And then if the exoskeleton supported them in this position, then that was a correct prediction. If the arm sank or started to float upward, then that was an incorrect prediction, and there needed to be some sort of modification. We also looked at some of the specific characteristics of the distance here and where sort of the arm pads were to identify whether or not the arm support or the arm support exoskeleton fit was predicted correctly. And so the results so far have looked at the fit prediction and support prediction separately, and you can see that the algorithms identified, the correct fit and support between 85 to 87% of the time across all the exoskeletons. These are 3 different types of exoskeletons, and you can see some had more success with these algorithms than others. But all in all, they were pretty darn close. We did find that the equations worked better for males than females. There was about an 8% reduction in correct predictions for females than their male counterparts. And so that's something that we can work on to try to improve. Okay, what we did after we were able to identify the correct fit and standardize the level of support was we created an obstacle course to evaluate safety and usability. We wanted to look at the impact of the arm support exoskeleton on maneuverability, balance, gait, climbing, and stair climbing. And I want to just add that we really weren't sure whether having the exoskeleton on or engaged or off, meaning the device is worn but not providing any support, would have an impact on some of these things. And so the question was, should people be wearing them? And can they wear them all the time? Can they wear them in certain situations? And if they do, is it really important for them to turn it off when they do certain activities? You can see that the person was asked to maneuver in narrow hallways, duck under things like scaffolding, step down onto a force plate from a step, and then balance on one leg, maneuvering through apertures of different sizes, and then going up and down a ladder as well as stairs. We looked at things like time to completion, number of errors. We looked at body joint motions, and then user perceptions. There were 40 participants, half of them who had construction experience, and the tasks included, well, we clustered the tasks into donning and doffing, maneuvering through constrained spaces, ambulating on a balance beam and around cones, and then climbing stairs and a ladder. Donning and doffing time was, pretty similar. It took a little bit longer to put on an exoskeleton than it did to take it off. And it took a little bit longer to put on the exobionics and take it off than the other ones, although it wasn't quite statistically significant. I think what was really interesting was that when they moved through constrained space, we did see that there was a difference. So for A, this is the Autobach, B is Suit X. This is Suit X in the off position. This is the exobionics on the on position and the exobionics in the off position. And then it's all compared to no exoskeleton at all. The blue bars are the amount of time that it took in seconds. You can see that on this left y-axis, and then you can see the number of errors here on this right axis. And so you can see compared to no exoskeleton at all, there were certainly more errors. An error would have been like a bump into the wall, or a stumble. If they were on the balance beam, maybe a toe down off the beam. You can see that it did take more time to complete the other tasks with an exoskeleton, but not quite as much, not a lot more time, but certainly some more time. That was more pronounced with the Suit X than the others, though really, no statistically significant differences. There really was no difference between the on and off settings. So wearing the same exoskeleton, say in this case, the Suit X, the time to complete the task and the number of errors was really not impacted by the support level being engaged or disengaged. And that was really the same thing for the exobionics. The Autobach does not have an off switch, and so that's why it doesn't have an off position or data presented here. We didn't see any statistically significant differences between the balance beam and figure 8, and we didn't see any differences on time or errors for those tasks. For the stairs and ladder, wearing no arm support exoskeleton was faster than wearing any exoskeleton. And it was close to being statistically significant, but not quite. The p-value was 0.06. When we had people step down onto a force plate, we did see, we looked at something called the DPSI, which is Dynamic Posture Stability Index. And that gives us an idea of how much movement there is in different planes. We also looked at the center of pressure path length, so how much motion they were engaged with or occurred with that step down onto one foot. There really wasn't a big difference between no arm support exoskeleton and arm support exoskeleton, but there was a difference between men and women when they were wearing the arm support exoskeleton. And so we thought that could be due to the fact that the arm support exoskeleton is just a larger portion of the female's weight than it is the men. Although we're still looking at more data to be able to confirm that. So to summarize from AIM-2, we found that increased maneuvering time in constrained spaces and climbing is recommended. There were increased errors when maneuvering in constrained spaces with an arm support exoskeleton, and that their increased time was really needed when climbing on ladders or stairs. And so these were essentially used to build some guidelines, or the start to some guidelines for exoskeleton use in construction work. We surprisingly did not see any differences between on-state and off-state. And so although we identified things like there should be caution when using an exoskeleton in a constrained space or climbing ladders or stairs, and that they might need more time to perform those tasks. At this point, we really wouldn't suggest that they need to turn it off when performing, different tasks. The next part of this laboratory study was to evaluate the optimal support based on the characteristics of the task. And so this project required someone to stand on this force plate, and they completed a drilling action either on the wall in front of them or overhead on the ceiling. As they drilled into one of these pipes, they got some visual feedback and auditory feedback to tell them sort of how much pressure and how long they should be drilling, and that was just to standardize the task. And so they did this in two different ways. One was static and the other was dynamic. So the static approach was going from pipe to pipe to pipe to pipe and never bringing their arm down to their side. Dynamic would be doing one pipe, bringing the arm down to the side, doing the next pipe, drilling into the next pipe and bringing the arm to the side. And we were interested to see if that dynamic work versus static work impacted their preference in terms of support level. So when we look at the information, this is data, muscle activity data from using surface electromyography. And we looked at 4 different muscles, or presenting 4 different muscles here: the anterior deltoid, the middle deltoid, the upper trapezius, and the infraspinatus. And then these colored bars represent no support at all, 50% support, 75%, and 100% support. And so again, that 100% support would be analogous to bringing your arms up at 90 degrees and letting your arm float completely in the arm support exoskeleton, and the arm support exoskeleton just holding it right there. 50% support would be half of that, and 75% support would be 75% of the torque required to float your arm. And because we had done that fit and support level algorithm approach, we could calculate this quite precisely for each person. You can see that the different support levels do reduce muscle activity in the anterior deltoid, in the middle deltoid, in the upper trap, and even in the infraspinatus, although some of the magnitudes were quite small, between 3 to 5%. Up to, say, 6%. These are the findings for the wall, and these are the findings for overhead. And again, because this is the static motion, this means that they were drilling overhead for the entire task, or drilling against the wall for the entire task. Overhead, you can see that the numbers are a lot larger. So it required, say, 26% of anterior deltoid muscle activity, 26% of someone's maximum voluntary contraction. With when they weren't wearing exoskeleton at all, or had zero support from the exoskeleton. And then you could see that with an exoskeleton with, say, 100% support, that muscle activity reduced to, say, 16% of the person's maximum voluntary contraction. And so this reduction is quite nice, particularly for the anterior and middle deltoid, less of an impact for the upper trapezius and infraspinatus for that static overhead work. When we're looking at the dynamic wall versus overhead, and again, this is median muscle activity, so sort of the average muscle activity while performing this task. You can see that in the wall, there's again an impact of reduced muscle activity with increasing level of support. And again, you see that overhead percent maximum voluntary contraction or muscle activity is higher than when using or doing the same activity against the wall. And again, you see this reduction in muscle activity even when performing this task dynamically. Now I wanted to show you the comparisons of the same information, but static versus dynamic. And so here you see that the muscle activities really aren't that different for static versus dynamic work. And this is for overhead. And we see the same thing for the wall work, that whether they performed the task statically or dynamically, there wasn't a huge change either in the magnitude of muscle activity or the change in muscle activity given increasing support provided from the exoskeleton. I think what was really interesting was what people preferred in these different tasks. And so here you see that for static wall support, meaning static wall work, more of them preferred the 75% support. And you could see that more people preferred 75% support for the wall, even if it was dynamic. So regardless of whether it was static or dynamic, they liked less support when they were doing work in front of them. And there were more people who liked more support or 100% support when they were doing overhead work, again, regardless of whether it was static or dynamic. And you can see that the rates of perceived exertion very much followed what we saw for muscle activity. There was a reduction in their rate of perceived exertion when performing these tasks, and greater so for the overhead work, regardless of whether it was static or dynamic. And so to summarize for this project, we looked at where we looked at muscle activity. We saw that it did decrease as support increased, and we expected this. This has been shown in other studies. But we did see that muscle activity was higher for overhead versus the wall tasks, and yet it was pretty similar for dynamic versus static tasks. The rate of perceived exertion did follow these reductions in muscle activity. And so we saw a reduced rate of perceived exertion as support level increased. And then the preferences indicated that 100% support level was preferred for overhead work, while 75% was preferred for wall work. And it really looked like the type of task, meaning dynamic or static, didn't impact their preferences very much at all. So then we took this information and we wanted to develop some preliminary guidelines and then evaluate the exoskeletons in the field. And we went back to our survey results to look at people's perceptions or construction workers' perceptions of training when they were trying new tools. And interestingly, 73 to 77% felt like in-person, individual group training was very to extremely effective. And, tailgates, those are sort of the short trainings that happen on a work site just before they go to work. Maybe that was only moderately effective. And then simulation, there were more people who thought that simulation might be effective way to train people on new tools. And so we looked at this and we thought that a few things would be really important when training people in exoskeletons. One is that individual or group would be important, and having them be able to simulate or try things with the actual exoskeleton would be important as well. In the field, we found that 64%, and this is a field evaluation where we gave them an exoskeleton and asked them certain questions after about an hour or two of use. 64% reported less physical effort, 55% reported less fatigue, 58% reported less discomfort, and about half thought that they should be standard issue for their type of work. And on a likely to use scale of 0 to 10, the average was about 6.9, indicating that they, were likely to use it for at least some of their work. And so we've been putting together different ways of training construction workers on what we found through these various laboratory projects, as well as how to, set up the exoskeleton and think about the task that they're going to be using it for. But we weren't really convinced that this paper approach was going to be enough. And so we've been developing a user guide that can teach people how to essentially do different things with their exoskeleton. So there's different courses. You don't have to take every single one of them. You can go to any one of the classes on here on the left. And the idea is to have this be specific to different exoskeletons. This one just happens to be the Hilti exoskeleton. And it's trying to break up information, some of which is available on the web. For example, this is actually from the Hilti website. But what we found was that people were pretty confused with those videos because they were a lot longer. And so we broke it up into smaller chunks and then put in some evaluation and questions to help people identify whether or not they've learned what they were supposed to learn from that. We also included an interactive guide to help them fit the exoskeleton. And so you can choose the make of the exoskeleton, the type of work, put in height and weight and your sex, and then click Get Recommendation, and you'll get a really nice, specific support level settings, arm length settings, spine length settings. And this is very specific to each exoskeleton. This was done by 2 interns this summer. I want to make a shout out to them, Dylan and Elizabeth. They did a great job of putting together not only this training, but also thinking about how we can evaluate the training. And so we evaluate it through learnability, efficiency, memorability, identifying errors that were made, and then looking at satisfaction and usability. And we asked people 2 different, we asked them about their user guide, their experience with the user guide, and then we also asked them about their experience with Hilti. And so each one of these evaluation criteria had certain specific things that we wanted them to be able to do to show that they had learned or could remember how to, say, fit the exoskeleton. And right now, we've done some preliminary testing looking at 5 users, looking at how much time it takes to complete it takes them to complete the guide, what their essential quiz scores were, how many errors occurred, and what their satisfaction usability score was. And you can see that this is for the ASE guide, and there were some changes that were made between users, and you can see that the usability went up and the number of errors certainly went down. For the ASE guide, you can also see that the number of errors went down, and then there was a particular issue with user 5, and so these are things that we're looking into more to see, okay, what went wrong when they were trying to fit the exoskeleton themselves and set the support level at themselves. You can see that the SUS score started to go up over time. And I think I just wanted to present this as a way to demonstrate how, even when we start with workers, getting their perceptions, go into the lab and start evaluating the efficacy of an exoskeleton, it's important to then go back to the workers and now evaluate what our recommendations are to make sure that they can actually use these in their own. We don't want these just used by, say, large companies who have a health and safety, full-time health and safety person. We also want them used by all of those smaller construction companies that make up such a large proportion of the number of companies in the US. We, again, are continuing to make edits, breaking up the videos into smaller little GIFs, and then, again, providing more feedback and more evaluation along the way. So in conclusion, again, I think laboratory research is needed to answer basic questions, particularly with something like implementing exoskeletons in construction. Again, the tasks are so varied, the workers are varied, the environments are varied. And so it's really important for us to know, whether or not it works before introducing it, and what the potential challenges and barriers would be. Translating the laboratory research findings into practice is really critical. And I think that asking the users along the way is really important, making sure that we explore different mediums to get the word out and to train users on how to use these, and then ensuring that we get consistent feedback. And I think that sort of brings us to the next 5 years of this grant, where we will be evaluating the exoskeletons in the field with different types of construction workers. And we'll be evaluating them for 2 to 4 weeks, all the way up to 4 months. And I think that will give us a lot of great information about the long-term impacts of exoskeleton use in construction. I do want to thank all the construction workers and all the students that helped support this project. And I also want to give a shout out to CPWR. A lot of the statistics that I showed in the beginning are from their data dashboard, which is fantastic. And they've been great partners in this. And if you haven't checked out their website, it's sort of a treasure trove of great information. And that's it. Thank you so much for your time. I really appreciate it. And want to again acknowledge NIOSH and CPWR for the support of this project.
So not only was attendance amazing for this, we were well into the high 180s, 190s, and even now it's about 180 people are still on. But there are 16 questions in the question and answers. So clearly this has struck an amazing chord. I will try and do justice. Clearly we're not going to get through 16, but we'll see how far we do get. So the first question was, would you consider these types of exoskeletons as PPE?
Oh, someone had to ask that. So this has been largely contested as, is it engineering control? Is it PPE? And ASTM, I believe, has decided that it's PPE, personal protective equipment. I don't think it's going to do very well in construction if we call it PPE. We asked people, what would you call this? And they want it to be called a tool. They want it to be a tool that's in their truck that they can pull out when the job requires it.
Mm-hmm.
Know what jobs are really fatiguing, for example, in this case, for the arm or for the shoulder. And so thinking of it as a tool to help them do a job is, I think, going to be a lot better than having them think of it as like mandatory PPE that they have to use.
Right. So second question, were other stakeholders like the auto industry accepted versus construction workers? How about the cost and availability for small construction companies?
I didn't understand the question about the auto workers. They were not included in the survey. The survey was very specific to just construction
Right.
workers.
The second part was the cost and availability for small construction companies.
Yeah, great question. So in the survey, we did ask what people would likely spend or what they thought their companies would spend, and it was around $500. Exoskeletons can cost a lot more than that, even up to $2,000. A lot of small companies have called me since we did the field evaluation, asking me if they could borrow an exoskeleton for a particular job because they liked it that much. And they had the idea of exoskeletons being available at like a rental agency. So, just like you would rent a jackhammer, you would go and rent an exoskeleton for a project. And I really think that that needs to be considered to make it more accessible. I do know that Hilti has some clever approaches to provide, to renting them essentially over a period of time so that it's like $100 a month to rent it versus, paying $2,000 right off the bat.
The next one said, in the post-COVID world, is there an issue maintaining sanitation of the skeletons, and how do we solve it? Might be a barrier for a company to implement since it's an extra cost.
Yeah, that's interesting. I feel like it's harder to keep them clean from like dust and materials than necessarily, being worried about viruses. Maybe that's short-sighted. But there are covers that are, available for like dust protection. And I'm sure you could do the same thing for, if you were worried about infectious diseases. I think they're also largely, you can take portions off and wash them, and you can certainly disinfect, the hard portions. So I haven't seen that as a problem. I do think sharing them, maybe sharing them with one other person might work, but I think people are probably going to want their own if they use it enough, or, if they're not using it very much, they might end up just renting it, in which case they'd sort of be accepting that risk anyway. And it could be clean, just like, a wetsuit or something else that is used commonly and rented could be cleaned.
Next question, for those that already have issues, would this be beneficial in improving injuries that already exist or just in preventing further injury?
That's a great question. I hope we hope to get more enlightened on the answer to that in the next 5-year grant. I'm not sure, we're not going to be looking at sort of the return to work process and giving it to someone who is injured and going back to work, but we certainly are going to be evaluating their acceptance and usability in people who have had longstanding issues in the past, or have maybe some pain, but haven't had like a rotator cuff surgery or something of that sort. So I think baby steps, and the first step is to make sure that when people are tired or in pain, we see what their response is to long-term use.
Next one, where are the most common barriers for uptake? Cost for the employer, resistance of workers to wearing?
Well, this next project will look at 2 to 4 weeks of use, as well as up to 4 months of use. I think that both cost and setup is going to be the most challenging. As we get more information, we can post information on like what support level, what tasks it would be appropriate for, and what support level should be used for different tasks. And I think that's the long-term plan, is to say, oh, okay, you're doing drywall today. Here's some recommendations on support level. And yes, this is a good task that you should use the exoskeleton for. It's going to take us a little while to get there, to that point. I think that the more we can have an individual take an exoskeleton, fit it to themselves, have resources to look up how to set it up support level wise and what tasks to use it for, I think the more people will use it.
Next question. When workers were surveyed, did any worker mention use of exoskeleton impacting their access to breaks? Maybe donning or doffing would make break times less accessible.
No, and once it's set up, it literally, we're in like the 30-second to 60-second realm of putting it on, taking it off. And so it's extremely short amount of time once it's set up.
Would continuous use contribute to muscular atrophy?
That has been a question and concern. I don't think so. And the reason I say that is because I don't think these are going to be used all day, every day. I think they're going to be selectively used for tasks that are really hard. In fact, we're seeing that people really don't want to use them when the task is not that hard. I didn't have time to present it today, but we did look at certain types of tasks like stapling cables compared to concrete grinding. Concrete grinding, they all really liked using it because the tool is quite heavy and it's really hard work. When they were using a staple gun, it wasn't as advantageous and it kind of felt like it was in the way. And so they're not going to use it then. So I just don't see it prevent or causing atrophy. I think that people are going to use it selectively for jobs that exceed, are very close to say their capacity versus using it all the time and then seeing some atrophy.
So I'm going to try and hone these down a little bit. Do you anticipate that some of the potential consequences wearing exos, errors, etc., will go down with practice?
Yeah, I do. Ours was it's a very good point that, people did have a little bit of practice time, but not much. And I think that as they wear it more, they likely will be, even more efficient and understand with sort of their body space requirements with the exoskeleton on more.
I think you answered the next one, which was the amount of average time for donning and doffing. To the next question, seems like the likelihood of use may change after an 8-hour day or week of use. This is when the heat can build up and other concerns as well. That's a comment. The weight force of upper extremities is transferred somewhere. I am assuming hips, lower back. Did you issue warning to those employees that have previous injury, to those individuals that have previous injury to the weight transfer location?
We didn't issue warnings at all. We did ask about discomfort and pain over the course of the trials, and we didn't see that as a large problem. But one of the criteria was that they had to be free of existing injuries. So it wasn't like we were trialing it on someone who had a really active back injury at the time. But it is a good point. It does transfer load. That can be a good thing to share the load. And, as that question mentions, maybe that's a bad thing if someone has a longstanding back issue.
So there are a few more, maybe you'll get a chance to answer them after. Michelle, I hope we can save these. In the interest of our audience, it's now 1 o'clock. This has been tremendous. And the fact that there were greater than 20 questions answered and close to 190 people attending is just stellar example of how important this work is. So thank you so much, Carisa, for this great talk, and to the audience for your level of engagement, which is extraordinary. Thank you all.
Thank you. Thanks everyone for coming and for your time.
Bye-bye.
Bye.